Hey, this is Mr. Beckstrom, and today I want to take a look at section 6.4. This is on the central limit theorem, and I'm doing a question that's very similar to the one I did in section 6.2 because I want to see how we can expand on the idea of the normal distribution questions, these real applications, when instead of just talking about the probability of a single member of a population being somewhere above or below the mean, I want to take a look at the probability of a number of more than one of members of this population being above or below the mean somewhere. So this is really kind of the essence um, of the central limit theorem, is saying what's the probability that 5 are this far above or that 3 are this far below, instead of just saying what's the probability of 1. All right, so let's start here. Given that the water, let's actually read the question first. Passengers died when a water taxi sank in Baltimore's Inner Harbor. Men are typically heavier than women and children, so when loading a water taxi, assume a worst case scenario in which all passengers are men. Assume that weights of men are normally distributed with a mean of 189 and a standard deviation of 39 pounds. The water taxi that sank had a stated capacity of 25 passengers, and the boat was rated for a load limit of 3,500 pounds. So question A says, given that the water taxi that sank was rated for a load limit of 3,500 pounds, what is the maximum weight of the passengers if the boat is filled to the stated capacity of 25 passengers? So that is just a simple division problem. So we take the 3,500 pounds and we divide by the 25 passengers. And we're going to get, let's pull our calculator up. So 3,500 divided by 25, it's 140. So that's 140 pounds per passenger. So pounds per passenger. All right. All right. The second one, B, if the water taxi is filled with 25 random selected men, let's say, for example, some team sport got on there, and it was all men that got on, or maybe I don't know, it's just it happened to be all men that day that got on the boat. And what is the probability that their mean weight exceeds the value from part A? And this is where we have to use the central limit theorem, because we're not just saying what's the probability that one random man is heavier than this 140 pounds. We're saying what's the probability that all 25 men have an average weight that's more than this 25, that's more than this 140 pounds, right? So here, this is where we have to use the central limit theorem, and really the only difference between this and what we've done before is that we just have to divide our standard deviation by the square root of our sample size, and everything else is pretty much the same. So let me show you how we're going to do that. And this is also on page 267 with all the formulas. So the mean is the same because the mean of the sampling distribution is the same as the regular mean, but the standard deviation of all of the sampling means is the normal standard deviation divided by the square root of the sample size. So here for B, I'm going to go ahead and make my nice little distribution bell curve. I'm going to put my mean right in the middle. They want to know what's the probability that our 25 guys have an average weight of over 140 pounds. My 140 pounds is somewhere over on the left side here because it's less than 189, and they want to know what's the probability we're exceeding it. So what is the shaded area of this part of the bell? So we already know it's going to be more than 0.5 because 189 to the right would just be 0.5. So So how do we do this? I'm going to do this both in the calculator and by hand. So let's do the calculator first. That's my preferred way. So I am just going to go to second vars, go to my normal CDF, which does my normal distribution. My lower limit is the 140. My upper limit includes the right tail, so I just put in a really large number. I just put in 100,000 here. My mean is 189. My standard deviation, remember, it's my normal standard deviation, but because I'm applying the central limit theorem, I have to divide by the square root of my sample size. And my sample size, or my n in this case, is 25. So they want to know the probability that 25 are the weight of 25, the average weight of 25 is more than this 140 pounds. Paste it in there, and look at this. 0.9999999998. So that is 0.99999, I think 98. Anyways, very close to 1. So what does this mean? How do we explain this to somebody when they say, "Hey, I've got my soccer team over here. There's 25 guys. Do you think that they're gonna put your boat over the 3,500 pound limit?" And you run some numbers and you tell them there's a 0.99999998 probability that you're going to put it over the limit, then yes, that's almost 100%. That's about as close to 100% as you're going to get in the statistical world. That means that almost for sure, unless we had this crazy rare, just really skinny, crazy sample that we just happen to pick, a bunch of really thin, kind of weird guys that I don't know. Anyways, yeah, you're never gonna get a random sample of men that are the average weight's gonna be under 140. I mean, it's gonna be 1 out of every billion times or something. All right. C. After the water taxi sank, the weight assumptions were revised so that the new capacity became 20 passengers. If the water taxi is filled with 20 random selected men, what is the probability that their weight exceeds 175 pounds, which is the maximum weight that does not cause the total load to exceed 3,500? Okay, guys, we're going to do the same kind of thing here. So, see, I am going to put out my nice bell curve here, right down the middle. I'm going to once again put my mean and right down the middle, and then I'm going to put my data value that we're talking about here. It's 175, which is somewhere to the left of my mean. It doesn't really matter where I put it. I just have to put it somewhere on the left. And they want to know what's the probability that 175 exceeds. That's more than, so I'm going to shade to the right of that. So once again, I should have a value that's greater than 0.5, but still less than 1, because you can never have greater than 1. Clean that up a little bit there. There we go. All right, so how do we figure this out? Well, we're going to do it in the same way. Oh, I meant to do that one by hand too. Let me go ahead and I'll do that right after I finish this here. All right, so let's go back to the calculator, and we're going to do it the same way. So second vars, the normal CDF, enter. So this time I'm going from 175 all the way up to, so this is where it starts. Remember, we're including the right tail, so I just put in a really big number because it goes all the way up to infinity. Same mean, 189, but this time my standard deviation is divided by the square root of 20, not the square root of 25, because my n has changed. All right, Put that in there, and I get a 0.946. 0.946. So that's is equal to 0.946. Okay, and so that means that there's almost a 95% chance that even with the revised numbers, that if our vote has all men, 20 randomly selected men, that 19 out of 20 times we're still going to exceed that 3,500 pound limit. So it's still not very safe. All right, so let's go ahead and do this one by hand here. So this B, let's find out how we can do this. All right, so first we have to convert this to a z-score. So remember, the z-score is equal to the x value minus the mean all over the standard deviation. And this is going to be equal to the x value, which is 140, over minus the mean, which is 189, divided by the standard deviation. Well, now remember, our new standard deviation is the 39 divided by the square root of our n. So let's put that value in there. So let's do 39 divided by the square root of n. So that's 7.8. So we're going to use 7.8 instead of the 39. And this is equal to 140 minus 89, 140 minus 89 divided by 7.8. Oh, I'm sorry. I did the first part wrong there. 140 minus 189 divided by 7.8. 7.8. And notice that that gives me a z-score of minus 6.28 or 9. 6.28. 6.28. So that means that with our converted new standard deviation, the one where we divide by the square root of our sample size because we're using the central limit theorem, that we are a little over 6 standard deviations to the left of our mean. That is huge. That is really far away. So when we pull up our chart, which is right here, it only goes to minus 3.5, right? So remember, so we're going to take this value here, and that gives us to the left, but we want to go to the right, so we have to take this, subtract that from 1, so that's where we get our 0.999. And it's just going to be pretty close to the same value here. It's going to be about as large as this chart will go. As large as this chart will go. All right, and then D, we just kind of answer that. Is this new capacity safe? No, it is not, because we still have a 95% chance, approximately, to be overweight. So that's it. All right, if you guys have any questions, let me know, and I hope you have a great rest of your week. Thanks.